Assalamualaikum. We are from Group 5. In this video, we will present the experiment 6, which is Bourdon tube pressure gauge. So before we start, I will introduce my team members. My name is Faiz Abdurrahman and my friend Muhammad Akmal Azizi and Muhammad Zuhairi. Okay, we start the presentation. So abstract part. For the overall view of this experiment is to calibrate a Bourdon tube pressure gauge using dead weights, and also we will establish the calibration curve of Bourdon gauge and determine the gauge errors. The objective is to calibrate a Bourdon tube pressure gauge using dead weights. Here we go to the introduction. Instrument calibration is one of the primary processes used to maintain instrument accuracy. It is the process of configuring an instrument to provide results within an acceptable range. Non-weights have been applied on a dead weight calibrator to apply pressure to a fluid for checking the accuracy of readings from a pressure gauge. Various types of pressure measuring instruments have been used to measure the pressure intensity at any point in static or moving fluid. One of these devices is the Bourdon tube pressure gauge. Bourdon tube pressure gauges are most widely used nowadays because of their reliability, compactness, low cost, and ease of use. It consists of a curved tube of elliptical cross-section bent into a circular arc. When pressure is applied to the tube, it tends to straighten out and the deflection of the end of the tube is communicated through a system of levers to a recording pointer. This gauge is widely used for steam and compressed gas. The pressure indicated is the difference between the system pressure and to the external ambient pressure and is usually referred to as the gauge pressure. Okay, that's all from me. I will pass to my friend.
Now we move on to theory and then methodology. First, the theory. The pressure intensity at any point in static or moving fluid can be measured using various types of pressure measuring instruments. One of these devices is the Bourdon tube pressure gauge. Bourdon tube pressure gauges are mostly widely used nowadays because of their reliability, compactness, low cost, and ease of use. It consists of curved tube of elliptical cross-section bent into a circular arc as shown in the figure 1. Yeah. When pressure applied to the tube, it tends to straighten out and the deflection of the end of the tube is communicated through a system of levers to a recording pointer. This gauge is widely used for steam and compressed gases. The pressure indicated is the difference between the system pressure and the external ambient pressure, and is usually referred to as the gauge pressure. As the Bourdon tube pressure gauge is used intensively, the stiffness of the internal component changes from factory setup, and therefore calibration is necessary to give correct pressure readings. Calibration means checking the pressure gauge reading against a very accurate device. One of the calibration devices that is available in our lab is so-called dead weight tester. The Bourdon gauge is the most popular pressure measuring device for both liquid and gases. It can be connected to a new source of pressure, such as a pipe or vessel containing a pressurized fluid. The connection can either be direct or via a small tube called a capillary tube. This means that it can be mounted at any convenient location. It is also very versatile in that it can be designed to operate over virtually any range of pressure. The burden gauge normally measures so-called gauge pressure is the difference between the pressure in the pressure source and the current atmospheric pressure. It can, however, be modified to measure difference in pressure between two sources of fluid. It can, however, be modified to measure difference in pressure between two sources of pressure. An example, pressure difference or differential pressure. The burden gauge is an indirect measuring device which depends for its operation on the density of the internal applied pressure to cause an initial bend tube, called a burden tube, to straighten. Because the measurement is indirect and it is necessary to calibrate the gauge before it can be used. The calibration consists of applying a known pressure to the gauge and noting the position of the gauge needle on the scale. The gauge can be calibrated in a wide variety of units suit the particular application, provided that there is linear relationship between actual pressure and the unit of calibration. Apparatus for this experiment is piston, burden tube, pressure gauge, and the weight. And the figure 1 is shown. We show the apparatus that used in this experiment. Methodology. Now we move to methodology. Piston was inserted into the cylinder carefully. Then the piston was rotated in order to remove the air bubble. The reading of pressure on the pressure gauge was recorded when there is no weight on the piston. All readings and calculations are recorded in Table 1. The dead weight, 0.5 kg, was placed on the piston and the reading of the pressure was recorded. The weight was increased until maximum 5 kg load by putting each dead weight on the piston one by one, and the pressure were recorded accordingly. The experiment was repeated in order to get the average reading. Here is how we construct the table 1, and this is our revised proposal. So for me, I will pass this present. That's all from me. I will pass this presentation to Zulhilmi.
Hi and Assalamualaikum. I will continue to the result and calculation. So this is the table of what we get from the experiment, from the mass added 0.0 to 5.0, and then we will do 3 experiments to get the average for loading and unloading. So this is the data for loading and unloading. As we can see, 0.0 we can get 35.3 for loading and 35.3 for unloading. For 0.5 mass added, we can get 34.7 for loading and 12 for unloading. For 1, we get 20.20 for the loading and 16.3 for unloading. For 1.5, we get 20.20 and 9.4 for loading and unloading. For 2.5, we get 16.18 and 2.0 for loading and unloading. And final 5 we can get 13.7 and 13.7 for loading and unloading. Okay. Next, we move to discussion. For mass of piston is 1 kg, area of piston is 3.171 exponent 10 negative 4. And then we go to theoretical pressure added with actual pressure. The formula is force added by the piston divided by cross-section area of piston, and we can get 30.9 kPa. So actual pressure added when mass increased by 0.5, same formula, and we can get 46.4 kPa. So we go to the calculation of percentage error for loading. Percentage error, the formula is gross pressure minus actual pressure, and divide by actual pressure, we time by 100. So we can get 35.3. For unloading, same formula, we get 35.3. Same calculation is repeated for the other mass. So this is the table 1. We can see this is a table 1. The graph figure 1 shows that the data of measured experimental pressure FMEA and real theoretic pressure PTH are very different when the weight is increased. The percentage of relative error for the theoretical and test pressure gauge is therefore high. The percentage error between the FMEA and the PTH may be caused by the errors that occurred during the experiment. So we go to the table 2. This is a table 2. What table 2 shows is the graph feature to indicate that there is a small difference between the estimate pressure FMEA and the real pressure PTH as the weight decreases. The percentage of relative error for the theoretical and test pressure graph is thus comparatively small compared to figure 1. The disparity between FMEA and PTH may be due to mistake in the execution of the experiment. So, the final is conclusion. Considering the differing degree of error during this trial, this particular attempt is not a successful way of calibrating the Borden pressure graph. To ensure proper calibration, the measuring tool must have a stable machine configuration that does not include errors such to the computer. In this experiment, due to many sources of error, this involved but are not limited to leakage, weak lubrication, trap air, mechanical exhaustion, poor weight calibration, differential dead weight mass, and general user error. Open repetition of the experiment. A completely sealed piston cylinder unit with a uniform range of lead weight should be used. In addition, a high lubricity solution can be used instead of water to avoid any limited movement. With this modification, the experiment can be replicated and re-evaluated as a consistent calibration process. That's all from us. Thank you.